Hello, hello. I hope you survived lab 3, and today we will continue congestion control. Last week, we saw that if we simply allow sources to send packets in the internet, we will have traffic jams, inefficiencies, and in the worst case, congestion collapse. We have seen that one needs to do something about it. In order to reach an efficient use of the resources, so we should deploy a congestion control mechanism that will make sure that the use of the network leads to Pareto efficiency and to some form of fairness, which can be max-mean fairness or proportional fairness or anything in between. Last, we have seen that one category of controls, which are called one-bit control or end-to-end controls, react to simply a congestion signal from the network by increasing or decreasing the rate at which sources are sending. And we have seen that if we want to look at the only possible ways that make sense, it is to do additive increase and multiplicative decrease. This is where we stopped last week, because if we do any other combination, multiplicative increase or multiplicative decrease, then we don't improve fairness. And if we do additive decrease, we make fairness even worse. So we will not converge to a fair allocation of the rates. So if we deploy such one-bit schemes, one conclusion is we should do additive increase, multiplicative decrease, which is more or less what is done in the internet, with some modifications that we will see in a few more minutes. But if we do this verbatim, if we do additive increase, multiplicative decrease, so AIMD, sorry for this acronym, but this is a well-known acronym that everybody will now use. And if we do this not in a toy scenario like I explained a few minutes ago, where I have simply one bottleneck link, but if I do that now in a more complex network where every source may have a different bottleneck link, then what do you think will happen? Is that going to lead to a fair allocation? Is it going to lead to max-mean fair or proportionally fair allocation? What do you think? Here you should simply give your best guess. Well, the poll is open on Speak Up as usual. I invite you to join it if you didn't join it already. The Speak Up number is on Moodle and it's 60845 in case you need it. I'm closing this poll. And the majority says max-mean fairness, with a small fraction also saying proportional fairness. Well, let's see what the reality is. Whoops. The true answer is none of the two. So we can analyze exactly what happens, such a control scheme, at least approximately, and the explanation is given in this document here, which is an elaboration of those slides that is mentioned on the Moodle pages of the course. With a bit more work, we can use what is called the method of the ordinary differential equation. We can interpret a scheme like the one we saw, additive increase, multiplicative decrease, as approximately something that can be modeled with an ordinary differential equation. And if we use that modeling, we find that it converges to maximizing a utility function that is given by this formula, logarithm of the rate divided by the increase factor, the increase term, which is R, and the decrease factor eta. So eta is 0.5, for example, in the internet. And R is by how much we increase at every round trip when we receive a feedback signal. So it's this. Now, if I plot this curve, this utility function, we obtain the blue curve here. We see that I plotted them. It's not an exact plot in the sense I have to rescale them. I rescale such that they appear in the same box, because when we maximize a utility function, the only thing that matters is not the function itself, but if I add a constant to the function, or if I multiply the function by a positive constant, it doesn't change the allocation. So we can rescale. And if we rescale here to have a fair comparison, we see that it is really between max mean fairness, which is the limit, as we have seen last week, of utility functions that go to a step function, and proportional fairness. So it is close to proportional fairness in practice, but with a bias that goes towards max mean fairness. So that's what we will get if we do this. So that's for the general theory, and we will see that the internet really uses this theory as all the deployments, with an additional twist, which is called slow start. The additional twist is because in all the analysis I did so far, I assumed that things are stationary. I assume that the scheme converges, and it converges to something that maximizes a certain utility function. But in reality, in particular, if flows are very short, the transient time may play a role. So it's very hard to analyze what happens exactly if we have very short flows. And in fact, it is quasi impossible to control from a congestion viewpoint the short flows. I mean, if a flow consists in sending 3 packets, then there is not much you can do about it. And the thing in the internet today is we should be able to accommodate short flows by having enough capacity. The control we're doing kicks in only when the flows start to be large, when we transfer large files or video interactive sessions, for example. Nonetheless, the AIMD convergence has a small problem, which is that it is fairly slow at the beginning here. So let me show what happens here. We've seen that's the example we saw last week when we had 2 sources, the green and the blue, that use AIMD, so they oscillate around sharing 50% of the capacity. Then the third source kicks in, and then the third source will eventually also force the 2 others to decrease, and they will converge all more or less to the same fair share, 1/3 of the capacity. However, if we zoom at what happened on source 3, so on the y-axis here, I'm showing the rate of source 3. So we see that it starts from 0, then it increases, but it takes a fairly long time. It takes several iterations to reach the fair share. So that is perceived as being too slow. Therefore, we accelerate this by another algorithm, which is called slow start. Now, the way I'm putting it, I realize is a bit counterproductive. I'm calling slow start something that wants to be faster than additive increase. But here, it's faster than an additive increase that started at 0. What happened in the internet before congestion control, so during the first 12 years of the internet, when it was not congestion control, before the first big collapse of it, then sources would send at the maximum rate, because if you open a TCP connection, the server will give you the congestion, will give you the offered window. If the server is not overloaded, it will give you the maximum window, which is given by its socket buffer size. We've seen sockets extensively those weeks through lab 3. So every socket has a buffer size, which is a few thousand bytes, typically 4,000 to 8,000 bytes. So this is how much you will receive at the beginning of a connection. So a TCP connection in those old days would start by sending with this maximum window, which means you can send a burst of several thousands of bytes. So 4 to a burst of a few packets. So that was considered a bursty start. So slow start was a response to this that wanted to start more slowly. So we pick the initial rate, not at 0 like here, not at the maximum value that the offered window would allow, but at something which is dictated by this algorithm. So slow start is in reality a fast start that starts small. It begins with a small value, but then it increases very fast. And the idea is to say, we want to taste the water. You're starting a connection. You're competing with other flows that are sharing your links, and probably you have one bottleneck link somewhere. So you want to push the others a bit to reduce their rate, to make some space to you. But you want to do that in a way that is not too slow for you, but is conservative. So what you do is you have what is called a target rate, which is the dotted line here. So you start the target rate at the max rate that your capability would give, which is typically given by a fixed number here, for example, 10 on this scale here. And then you will increase the rate exponentially, which means that whenever you receive positive feedback, so you start transmitting, you start with a very small value. For example, you start with 1 packet, a window of 1 packet, which means 1 packet per round trip time. Then you receive feedback, which are acknowledgements typically. When the feedback is positive, you multiplicatively increase the rate here. So you increase the rate by a factor of 2 here. So you double the rate for every round trip time when you receive positive feedback. So of course, this will give a very fast increase. By doing that, you're increasing the rate at which you're sending. Sooner or later, you will hit the capacity of the link. You will start hurting the other flows that are using this, and you will receive negative feedback. When you receive negative feedback, you do the following. You look at the rate that you had, so this rate of 5 here in whatever unit, and your target rate becomes half of it, and then you restart. You restart from the smallest value, you increase exponentially until you reach that value here. So the effect is, if the maximum you had set to yourself here was feasible without hurting the others, you will go to that value and you will reach it. That means there's no bottleneck for you in the network. If there is a bottleneck somewhere in the network, you will hit it, but you will be conservative. You will not go to it and push all the others by say, hey, go away, here I am. No, you will first taste it. You will say, oh, this is where I should be trying to go. So we'll try to go there. But since you've had a loss here, we apply implicitly, in addition to that, the principle of multiplicative decrease. So we decrease, and then until we reach that value. So we consider that this value would be the fair value for us to start. So it is both reaching 2 contradictory requirements. First, go very fast if it's possible, but at the same time, do not do too much, do not exceed your fair share. So this is the algorithm that I've explained here. And let's see what this would give on this example here. Now, if I have slow start, if you remember, this is what this, this is what this source was, doing. If we don't have slow start and we start from 0, so source 3, which is on the y-axis, needs many, many iterations to reach a decent rate. Now we see that with slow start, in very few iterations, it will start oscillating around the share value here. And we see that here in this other diagram that shows it showing time on the x-axis and rate on the y-axis. The source 3 is the red one. We see that in very few iterations, it joins the other. And so they all now are in synchrony after less than one of these big increased times, which is here order of 100 time steps here. So this is the comparison I wanted to make. We see that very clearly slow start is a very fast start. Voila, those are the theoretical pieces that are underlying what is done in the internet. Congestion control is necessary to avoid inefficiencies and collapses. We should aim at allocating rates according to some form of fairness, which, if we use a good fairness property, will be Pareto efficient. And in the internet, the ideas that have been around and are used are AIMD and slow start, with, of course, a zillion other refinements that we will now discover. So in the second part, so what we've done so far is essentially theoretical and applies to all kinds of aspects in networks. But the major application of this is in the congestion control of the internet as implemented in TCP. So we've seen TCP in the transport layer module. In addition to what TCP is doing, which is a transport layer function, it is also doing congestion control. So TCP is used for congestion control. So why do we do that? Well, it comes as an afterthought. As I mentioned, when TCP was designed, it was a truly transport layer function. And the goal of transport is to help the application, make the interface between the application and the network. Now here, we piggyback this with an additional function, which is control the amount of traffic that goes into the network. It's really a network layer function. But it cannot be done in the network layer easily because it's flow-based, so it is done in the transport layer. And it is done mandatorily in TCP. So in addition to what we have seen, TCP adjusts its window not just to react to the offered window, the advertisement done by the destination, but also it computes a counter, which is called the congestion window, that will be used to limit the window size. The source of feedback is essentially losses. Essentially, not really, we will see that the internet is moving towards introducing explicit congestion notification, which is the bit of feedback which is not a loss, but this is being deployed slowly. When TCP congestion control was deployed, and the majority of deployments today use losses as negative feedback. That means when a TCP flow receives acknowledgements, it interprets it as positive feedback. When it detects a loss, of course, you do not receive a negative acknowledgement. It is just the detection of a loss that is the perception of the negative feedback. Now, why is that done in TCP and not in UDP? Well, the initial idea was that when this happened in the mid-80s, UDP sources were primarily sources that were sending very small flows. For example, a DNS client sends a request and expects an answer. So you don't want to congestion control this, other than if the answer doesn't come, you slow down the rate at which you try again, but you don't want to do much more than that. Today, things are different. There are many UDP sources that can be used to do their own congestion control. For example, a large fraction of the internet in volume today is using QUIC, which is a TCP, a UDP framework that replaces the transport layer in a different setting. Then and also you have UDP sources when you do, for example, interactive video. So Skype or other interactive video sources use a mixture of TCP and UDP, and they try to use UDP when they want to have very short response time here. If you use UDP sources that send significant amounts of traffic, high volume traffic, then you should do also congestion control in those sources. And we will see that there are two ways of doing this. One is to do the same as TCP friendly. This is what, as TCP, this is what QUIC does. This is appropriate if your UDP source has concepts similar to TCP of acknowledgements. Otherwise, you have to do different ways. We'll talk about it at the end of the course. This is what Skype would do, for example, with the TFRC protocol. We'll talk about this later. Right now, we will discuss how TCP does it. TCP comes in a zillion of versions. In the lab, we will try 2 or 3 of them. The popular versions of TCP today are TCP cubic, which is based on TCP reno, which is the historical version, which is still deployed a lot. And there's also DC TCP used in data centers that we will use in the lab here. Today, we will first start by discussing TCP reno, which is as I said, the historic version, which also serves as the congestion control of QUIC. So TCP reno, as you can guess, uses AIMD, additive increase, multiplicative decrease, and slow start here. Then the idea is that by adjusting the window size, we approximately adjust the rate, because the rate is approximately given by the size of the window divided by the round trip time. For the round trip time, there's not much we can do about it, but we can control the window, and this is a way to control the rate. So the window size that TCP uses is not just equal to the offered window, but the minimum of this and of a locally maintained counter, which is called congestion window. There is one congestion window per TCP connection at the source. It's computed at the source. The offered window is just obtained from reading the ACK, the window size in the TCP headers coming from the destination here. Then when we detect a loss, at least in the general case, we interpret that as a negative feedback and we apply multiplicative decrease. In TCP reno, the multiplicative decrease is by 0.5. When we have no loss, which is interpreted as positive feedback, then we increase the rate by 1 packet, and we do that once per round trip time. So we simulate the model that we have of the deck bit that I mentioned last week by assuming that once per round trip time we receive some feedback. Positive feedback we don't really receive, but we observe whether there is no loss, and if there is no loss, we more or less increase by 1 ms. How this is done exactly, I will describe in a minute. We also do slow start with exactly how I showed it a minute ago with the increase factor of 2 per round trip time. The terminology is when a loss is detected by timeout, when a loss is detected by timeout, not just slow start is at the beginning of a connection, but as we will see, we'll do it also when a loss is detected by timeout. Is a loss is detected by fast retransmit. Those are the two major ways of detecting losses. We will use fast recovery. We'll discuss that in a second. So how does TCP do it exactly? Well, the multiplicative decrease is obtained by simply multiplying the congestion window by 0.5. But as we will see in a second, when a loss is detected, we also do something special. So we just store this value in something which we can interpret as a target rate or a target window, which is called a slow start threshold, typically everywhere. So this is the decrease by 0.5 that we've done. The additive increase is done by this formula here. For every ACK that is received, we increase the congestion window by this formula. The congestion window is incremented by the size of a packet, MSS is the maximum segment size, square divided by the congestion window. Why do we do that? Well, if we interpret this formula in MSS units instead of bytes, TCP counts in bytes. So the congestion window counter has to be interpreted as a number of bytes because the TCP window is always in bytes. But if we would, as a thought experiment, interpret that as entire packets, so our unit of data is the packet, then we have to divide everything by MSS, and that gives that it is the same as increasing the congestion window in packets by 1 over the congestion window. Why do we do 1 over the congestion window? Well, it's based on the naive or brutal approximation that says if during one congestion window everything is okay, you should receive a number of acknowledgements that is equal to congestion window. So you will increment this by congestion window time, so you will add 1 to the congestion window. Of course, you will not do that exactly. Let's see an example. We start with a congestion window equal to 1. We receive an acknowledgement, then the congestion window becomes 2. Then we send 2 packets. We can send now 2 packets in parallel if there is no loss. We will receive 2 acknowledgements. We will apply the formula. For the first received packet, we will add 1 over 2.5. For the second received packet, we will add, for the first one, we'll add 1 over 2 That leads us to 2.5. For the second acknowledgement, we will increment and lead to 1 over 2.5, which will give an increase of 2.9, etc. So we will increase a bit more slowly than additively. We see we don't reach 3 here, which is what we would have had. It's a bit more slowly because of this formula, and also because the time it gets to do the increase is slowing down. We need a full window. So at the beginning, we needed 1 packet to be sent and acknowledged. Here, we need 3 packets to be sent and acknowledged, which takes a little more time. So we increase a bit less than 1 packet per round trip time. But approximately, this is what is done. So this is what TCP reno does for the increase thing. Now, TCP reno also does slow start. In slow start, we do multiplicative increase. Here, the multiplicative increase consists in, for every acknowledgement that is received, you increase the window by 1 packet. If we see what happens here, we will see that that really leads to an exponential increase. If I start with 1, then I will increment and go to 2. Now I can send 2 packets. When I've received 2 packets, I see increment first by 1, then by 1. So I have doubled my window here. And when I send 4 packets here, by the time I've received all the acknowledgements required to send the 4 packets, I have doubled my window. So we multiplicatively increase the window. It's a bit more slowly than multiplicative decrease, because the time it takes is also increasing, but roughly speaking, this is multiplicative increase. So this is what TCP reno does, with an exception. That is that when a packet is lost and detected by timeout, the reasoning was perhaps because this congestion control was introduced after a complete collapse of the internet. So people became very, very nervous about traffic control issues, so they wanted to be extremely cautious. So what is done is, when you have a loss, then you detect that you've created some damage somewhere. So you want to be very careful. So you start with slow start again. So the first response to the congestion collapse was to do that. Whenever you detect a loss, you go into slow start. You don't simply apply the multiplicative decrease of the window. You apply the multiplicative decrease to the target window of the slow start, which is shown by the dotted line here. So we see when the connection starts, the window increases exponentially fast until you obtain a loss. Then you remember the value you had, and this gives this dotted line here. You go into slow start, and if this was truly the rate at which a rate that is in the region where you should operate, then you increase again in slow start. And if you were guessing right, you do additive increase in this period here until you will hit a loss, in which case the story will go on again and again. So we see that the additive increase is in fact continuous when there is no loss, and the multiplicative decrease occurs in a complicated way through the form of, when before the loss you target half the window that was occurring before the loss. This is how additive increase and multiplicative decrease is really implemented, combined with slow start. Originally, this was the only thing that were done, but of course we know that most losses are expected to be detected by fast recovery and not by a fast retransmit, and not by timeout. So the idea is that when we detect a loss by timeout, this is the last resort. Fast retransmit has been deployed, has been invented to avoid this. So the assumption that is made here is that when we are really in stationary regime, then most losses should be detected by fast retransmit, and we should not do slow start. In contrast, when we detect by timeout, we think that's a more severe loss, perhaps because the network condition has changed, or we had been inactive for a long period of time, so we don't have much information about what the status is, so we should be more careful. Otherwise, if we detect by fast retransmit, we're receiving, remember that fast retransmit works when we continue receiving a lot of acknowledgements. So we have positive information that comes. So we will not do slow start. However, there's a small problem here. The formula that the rate is equal to the window divided by RTT is true when there is no loss. When there is a loss, then there are side effects of the window. And in particular, typically when there is a loss, that means some acknowledgements have not been sent. So the window, even if the window remains the same, the rate at which we're sending is reducing because we cannot use the full window, because the principle of the sliding window implies that all the sent packets that have been sent and are in the window cannot be sent, are blocking the window. Let's see an example to explain how this happens. I'm showing here a time-space diagram. On the first axis on the left is time at the source. On the axis here is time at the destination. This is one TCP connection. Of course, in a TCP connection, both ends are both source and destination, but I'm zooming here on the left being the source here. And assume that the packet size is 100, which is very atypical. Packet sizes are typically larger, but that makes the explanation simpler. And assuming the max duplicate axis 3, that means fast retransmit kicks in when we have 3 duplicate acts. So source sends 1 packet. The window is 800, and this is both the congestion window. This is the size of the congestion window. I assume the offered window is much larger than that. It is 1000 here. So it's always the congestion window that will cause a problem here. The bottleneck is the network, not the receiver buffer here. So we can send 8 packets, and we start sending packets. We send 1, 2, 3, 4, 5 packets. Packet 2 is lost here. Then we receive an ACK for the first packet. But we don't know yet that there is a loss here, right? The loss will be observed when we receive 3 duplicates hacked. So it will be received at time 12 here. So at time 6, we apply the principles of TCP. We do a bit of additive increase. We increase by 1 over the window size. That gives this small increase of the window, no big deal, but at least it doesn't decrease. And we can continue sending packets. So the source sends packet 6 and 7 and 8 here. We receive ACKs that are duplicates ACK. The ACK field doesn't increase. Of course, there will be a SACK field here that I'm not showing because I'm not interested in that at the time being. And then I receive this third duplicate ACK here. So here I've detected the loss here. Now, by detecting the loss, I should decrease the window divide the window by 2. The window was this. I divide by 2. In round terms, it gives this. That is the window that I would obtain. Now, here comes the problem that arises from the fact that we use a window to control a rate. Other networks, like DECnet, for example, were using rate control. Also, cellular telephony networks use rate control. If you use rate control, we will see at the end that this can be done in Linux with traffic control issues. You use things like leaky bucket controllers or other forms of scheduling mechanisms. This can be done here, but this is not what is done typically in the internet today. It's done only in industrial networks or cellular networks here. So when we control the rate by the source, it works well when there is no loss. But when there is a loss here, there's a side effect here. The window is 400. The source has, if the window would be 400, right? Then the window has sent already 5 packets. So with a window of 400, and those packets are not acknowledged here. The first is acknowledged, but there are all the following 6 packets, or even 7, that are not acknowledged. That means that if we abruptly reduce the window, it's in fact stopping the source. So by halving the window, dividing the window by 2, we're not reducing the rate of the window by 2. We're putting it to 0 in this case. So what should we do in general? The answer is very hard to know. In practice, we know that if we reduce the window, then we might block the source. So what should we do? Well, this is what fast recovery does. Fast recovery is the name of the algorithm that tries to mitigate this problem by allowing the source to send, in fact, by increasing the congestion window very fast, in fact, multiplicatively. So we remember the target window that is still called slow start threshold, even though this is not a slow start, which is 0.5 of the current size of the window. This is the target window size. This is the 400 we had on the previous slide. And then we increase the window by adding first 3 packets. And for every duplicate ACK that's received, we increase by 1 packet. Excuse me. This is not COVID. I did a COVID test 2 days ago and it's negative. So we see here that at point 12, when we receive this triplicate, this third duplicate ACK, we increase the window by 300, so it becomes 700, which is now large enough to allow the window to the source to continue sending. It's a bit larger enough. Is it good enough? Then we don't know. But in order to know what is good enough, we have an adaptive algorithm that will increase the window when we continue receiving acknowledgements. If we receive acknowledgements, that means the flow is still going on. So that makes some sense to continue increasing here. We will increase exponentially fast, which, as we have seen, means here increasing by 1 MSS, 100 bytes for every packet that's received. So here, the window, the congestion window, will increase here to 900. So what are we doing? We're increasing the window, and the reason we're doing this is because we need to increase the window to keep that source from sending. We want to keep that source sending because all we want to do is to reduce its rate to 1/2, but not stop it. So we will give an opportunity to this source to repair this loss, which will be done at this point here, is done at this point here. The packet was repaired here. And when the acknowledgement is received, at this point here, the acknowledgement is received, that means the loss is repaired, then we exit this exceptional condition, and we set the congestion window to the value that was cached here. That was the target value called slow start threshold. So the congestion window becomes 400. So the congestion window is apparently much smaller here than there, but it doesn't mean the rate is much smaller because now we've repaired the loss. That means we can really send at a rate that is given by this divided by RTT, whereas before we didn't know exactly what was doing, but if we had set this window at this point, we would have set the rate to 0. So this is what is done in the internet. Do those parameters work well, where extensive simulations were done and measurements were taken, and a number of SIGCOMM papers were done on this topic to see that, roughly speaking, it works well. But of course, it's not an exact value. So if we would continue this example, at time 20, here, if the source has much more data to send, can it send it? How many new segments of size 100 can the source send at this time here? The poll should now be open on Speak Up. I close the poll. The majority is not always right. The correct answer is C. See here, the window is 407. And the last ACK that has been received is 900. So we can send packet starting at, so which means this packet has not been acknowledged. So it counts as one packet. So we can send 3 more. So the correct answer is 3 here. Voilà. No, voilà, yet another question. Assume now we put Wi-Fi into this picture. And as you know, Wi-Fi, in particular if you're moving, if you're mobile, or if the environment is mobile around you, Wi-Fi might fail. You start transmitting. We've seen that with Wi-Fi, we do a CTS, RTS, etc. But that assumes that between the CTS, RTS, things have not changed and the procedure may fail. If that fails, what will happen now that we combine with TCP congestion control? I close the poll. Okay, I lost the connection. Okay, I give up closing the poll. The correct answer is, unfortunately, B. B here. The source thinks it's a congestion loss and reduces the window. So that's a major problem in the internet. In fact, we would love to have answer A, but there is no way a source knows whether a loss is due to congestion or is due to something else. And this is why, if we have this Zoom session over Wi-Fi, it might well be that the performance is much less good than over Ethernet because of this. The throughput of your Wi-Fi connection might be several megabits per second, which in principle is very good. But the congestion control will kick in whenever there's a problem with Wi-Fi. Your congestion window will reduce. Right? So that's one of the major issues. Also, for example, if you're downloading content from the other end of the world, and if there is a loss on your Wi-Fi link, then TCP will think we need to reduce the rate, so you will have very low rate, which is not at all desirable. This is why, for example, there are a lot of content distribution network. The internet is forced to push the content close to the users in order to avoid this and other similar problems that we will discuss again. So that is bad news, but this is how things are. We can mitigate some of it, but essentially you should avoid to have losses in any data path once we have congestion control of the the way it is in the internet. And there is no indication that this will change anytime soon. So we have to work hard on avoiding packet losses. Right? Now we could ask the similar question as we asked before. So what do we achieve in the light of the theory we did last week, what is TCP, this form of TCP reno, really achieving? Well, the answer is, well, it's close to AIMD, so we expect that the answer should be close. So this has been analyzed. So this version that I've described of TCP reno, using the same method, we find another utility function, which is given by this funny formula here. Here I plotted on a similar scale the AIMD function, the function that was that we saw a few minutes ago, and this function of reno. So we see that the small differences that there are between reno and AIMD are negligible. There's a small difference here, but it's completely negligible. So what's the take-home message of this? Well, this form of TCP implements a form of fairness that is close to proportional fairness, but with a bias towards max-min fairness, which is very good news. It means that the internet is really in good shape with this, in the sense that we have achieved distribution of the rates of all the users who want to share the capacity of the internet in a way such that we achieve something Pareto efficient and very close to proportional fairness, with a small small bias towards max-min fairness. Since both forms of fairness can be argued, this seems to be perfectly okay. There's still a residual problem that we will discuss in a few minutes after the break. So we interrupt the lecture now for 13 minutes and come back at 1:15.